So thinking outside the box, we have to pretty much look at, is there a number that I can maybe do is there something I can do to 1 and then multiply it to 1 to get 0? Well, if I think about it, if I do 1 minus 1, that becomes 0. And then 1 times 0 is 0. So take this and subtract it by 1, get another number, and then multiply that number to 1, which would give me this. Let's try this here. If I take 2, and then 2 minus 1 is 1, so 2 times 1 would be 2. Okay. If I do take 3, the next number here might be 3 minus 1, which is 2. 3 times 2 is 6. Over here, 4. If I do 4 minus 1, that's a 3. So 4 times 3 is 12. The pattern somewhat holds. So I have 1 times 0 would give me 0. 2 times 1 would give me 2. 3 times 2 would give me 6. And 4 times 3 would give me 12. So if I have this pattern, then how do I write it using n? Well, the pink number, our first number here, that's our term. That's the 1, the 2, the 3, the 4. So we can call that guy n, right? So the number of the term is n. But then how do I represent the number in the green? The 0, the 1, the 2, the 3. Well, I have to think of it in terms of the n. I got 0 by taking this n and subtracting 1 from it. I got 1 by taking this n and subtracting 1 from it. I got 2 by taking this n and subtracting 1 from it, and so on. So our green term can be gotten by taking 1 away from n. So we can define the green term by 1 less than our n, which is just n minus 1. So my pattern is n, our pink term, times n minus 1, the green. So in this case, there wasn't a constant number that we were multiplying by. It was a manipulation of n. So we were doing n, our term, times the term minus 1. So sometimes we're going to need to think outside the box that way. Like I said, this is probably going to be the hardest part of this. If we do move on, okay, let's talk about series now. Now, series is when we take the terms of a sequence and we add them together. So whenever you see series, okay, we're adding things together. So we literally take the list of the terms, aka -1, -8, -27, -64. And if this was a series instead of a sequence, it would be -1 plus -8 plus -27 plus -64. Or if this was a series instead of a sequence, it would be 0 plus 2 plus 6 plus 12. So with a series, yes, you do get a sum. You get an n value. Now, our series can be finite, meaning it's a specific number of terms, or it can be infinite, meaning it's never ending. So we have notation and symbols that represent a series. And this is called a summation notation. Now, summation notation uses a Greek symbol, and this Greek symbol actually represents a Greek letter called sigma. So it is sigma notation. And it looks like, and you might know this from Greek, like, you know, fraternities or sororities, this is called sigma, and it's kind of written like an E. So we start here, we go over like an E, we do a little corner in the middle instead of a line, come over and go straight back up. Now, the placement of things here is very important. The number that we usually put on the bottom, that's the term that we start from. So usually we start from n equals 1, the first term. The number that goes up here is the last term that we need. So if we want to add the 10, like the first 10 terms of a sequence, we would go from 1 to 10. And the rule is the formula or the function or the equation that gets us the values in the series. So summation notation here, again, we have our sigma. At the bottom is the starting term. The top is the ending term. And this is the rule, aka formula, with which we get our actual values. So if we take a look here, just definition of finite and infinite series. Finite series here, we have 2 plus 4 plus 6 plus 8. Again, this tells us it's a series because we have the pluses in between the numbers, not commas. Now, finite series has an end. So this finite series only has 4 terms, 1 to 4. 1, 2, 3, 4. So if I wanted to write this finite series in terms of summation notation, okay, I write my sigma letter here, my sigma nice and big. I have 4 terms, 1 through 4. So that means my starting term is at n equals 1. The last term that I have there is the 4th term. And the rule here is, well, it looks like if I have 1, this is 2 times 1, 2 times 2, 2 times 3, 2 times 4. So my rule is 2n. So writing this in sigma notation, I have my sigma, my starting term, my ending term. Normally, when you are writing sigma notation, if you're given this and you need to write this, your starting term will be n equals 1, or whatever variable you want it to be. You could use m, you can use I, you could use j, k, elemental p, x, y, z. It really doesn't matter. You can use any variable you want here, as long as you're matching up your variables here and here. So here is your sigma notation, aka your summation notation for this finite series. Now, if your series is infinite, aka you have this plus and then you have that dot, dot, dot. That's literally the main difference here. The plus and the dot, dot, dot. What changes is the end part. So infinite series never ends, which means at the top, you are going to have an infinity symbol because it's infinite. It never ends. So you still have it starting at 1, again, n equals 1, or in this case, notice I'm using the letter I, so I changed this guy to I. So same exact series, 2, 4, 6, 8, except this is now infinite because of the plus dot, dot, dot. So my rule is still 2 times my placement, so 2i. We start from the first term, and we do not have an ending term because it actually never ends. Okay, and here is the breakdown of how we figured out that rule. Okay, so in the main difference here is instead of having n equals 4 for the last term, we don't have a last term here, so it is infinite because of the dot, dot, dot. So if I want to write each series using a summation notation, the first thing I need to do is, number 1, determine, is it finite or infinite? So let's take a look. Over here I have 25 plus 50 plus 75 plus dot, 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 but then I have a plus 250. That's my last term. Okay, there is no dot, dot, dot after the plus 250. So that means this is a finite series. And once I figure out the pattern from these 3, I can work backwards and figure out which term is this ending at. Because it's not 1, 2, 3, 4. There's a whole dot, dot, dot here. So I need to figure out which term is this? How many terms in did I go to get 250 here? So if we take a look, our placements is 1, 2, 3. What can I multiply or add to 1 to get this? Well, if I do 25 times 1, I get 25. Let's see if that holds. 25 times 2, 50. 25 times 3, 75. Looks like I have a pattern. 25 times 1, 25 times 2, 25 times 3. So then you ask yourself, what do I have to multiply 25 to get 250? Well, 10. That means that this series goes from 1 to 10. So we start at 1 and we end at 10. And the rule that we have that's happening is 25 times n, or the placement of our number. So we have 10 on top. We have our sigma here, summation notation, n equals 1 because we're starting from the first term, all the way to the 10th term in the series, and our rule is 25n. That's your summation notation. Okay. Similarly over here, so let's take a look here. Notice we have all of this plus dot, dot, dot. There's nothing after the dot, 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 unlike here. That means this is an infinite series. Okay, so our summation notation will be starting from 1 and going to infinity. Okay, now for the rule, notice you have 1 over 2, 2 over 3, 3 over 4, 4 over 5. So if I take a look at my placements, this is my first placement, my second placement, my third term, my fourth term. Okay, so I can see that my terms are present here at 1, 2, 3, 4. These match up. The denominators, however, are always one more than what's on top. So one more than what's on top here. So again, this is just like the other example where we have n on top and we have n plus 1 on the bottom. So instead of subtracting now, we're adding 1. So our rule here for our summation notation is we have our summation from n equals 1 to infinity, because we're infinite, of n over n plus 1. Okay. Now, what happens when we have find the sum? We're given our summation notation, and we want to find the sum of this value. So you have to notice a few things. First, the rule. This is 3 plus k squared. Okay. They give you your starting point at k equals 4. They give you your ending point at 8. That means we want terms 4, 5, 6, 7, 8. So how do we do that? We take each one and we plug it in just like we did on the front page. So k equals 4, that's our starting point. 3 plus 4 squared, that gives us 19. K equals 5, k equals 6, 7, and 8. We get every single one of our values, sorry. Okay, so by plugging in 4 through 8. That's not your answer though. A sum means add together. So now we're going to take each one of these and add them together. So 19 plus 28 plus 39 plus 52 plus 67 gives us 205. So the sum of 3 plus k squared from k equals 4 to 8 is 205. So we're doing this exactly like we did on the front page when we were finding our terms. Similarly over here, look over here. We have summation of 8i from I equals 1 to 5. So we start at 1, we end at 5. So we go ahead and we do I 1 through 5, and we plug it in for I here. So the first term, I equals 1, 8 times 1 is 8. I equals 2, 8 times 2 is 16. I equals 3, 8 times 3 is 24. I'm literally using this formula right here, this rule, and I get each one of my terms. And again, this right here, every time you see these, this means add them together. This means add them together. I'll say it again. The summation notation means add them together. So you found your terms. Now you add them together and you get 120. Okay. Pause this, get down what you need to get. Here's your exit slip for the day. You'll need to put in these answers into Google Forms, and I will have the link for you right under these videos.